Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on October 23, 2025, about 2 days ago. The headline is a scalable recurrent memory called Kinaema that keeps O of 1 update and read cost as history grows, letting an agent locate a goal image relative to its current pose and outperform recurrent baselines on long sequences. The paper is titled Kinaema, a recurrent sequence model for memory and pose in motion. And, as we will see later, the results are really impressive. In short, this paper introduces Mem-Nav and shows Kinaema boosts navigation success and relative pose estimation while staying compute efficient over long horizons. Alright, the previous segment introduced the motivation and the key promise. Figure 1 presents the full pipeline. A visual input stream flows through an image encoder and a recurrent transformer, which compresses the sequence into a latent memory MT. The query image passes through a separate encoder, and a decoder reads from memory to estimate the relative pose. That pose then conditions the downstream navigation agent, so the agent can act using cues gathered before the episode begins. Well, Figure 1 sketched the pipeline. Figure 2 explains how the recurrent memory actually updates. The model stores memory MT as N by E embeddings, which get contextualized with the current image and odometry passed through a linear layer and a transformer to produce update candidates. A GRU-style gating block, with weights shared across embeddings, selects how much to write, so capacity scales without bloating the gate. The read step reshapes memory into YT for downstream decoders. Okay, Figure 3 connects the memory module to the navigation policy. The diagram shows how Kinaema updates memory with the observation and odometry, then reads embeddings to produce a relative pose estimate, which serves as a goal direction. The right side integrates this with a binocular encoder that compares the goal to the current view, so the policy gets both visibility cues and memory cues. A recurrent block keeps the agent's own hidden state while actions are predicted. Alright, the previous figure tied memory to policy. Figure 4 shows how accuracy changes as sequences get longer. Both models were trained at length 100, and the curves evaluate from 100 to 1000 steps. Kinaema stays consistently above the GRU across all thresholds, which means the recurrent transformer memory degrades more slowly. Accuracy drops as length grows, then stabilizes around mid-range lengths, with a small late uptick, but Kinaema maintains a clear margin. So, while Figure 4 compared length generalization, Table 1 reports head-to-head Mem-RPE accuracy and memory cost. Kinaema tops every column, scoring about 21, 41, and 63 at sequence 210, 21, and 37 at sequence 800, which shows strong long-horizon recall. DRU comes next, but lags by a clear margin. Truncated history and large XLSTM trail further, and Kinaema does this with a modest 61,000 memory size. So, while the previous table compared accuracy and memory cost, Table 5 reports navigation SPL across difficulty and scene splits. The rows show that the inject H0 baseline fails to capitalize on priming, whereas a dedicated GRU memory helps. The Kinaema row delivers the best SPL, with gains of roughly 2 to 10% on the harder bands, which indicates stronger goal localization from long priming. The primer column confirms that having a primer boosts performance, and the boost is largest with Kinaema. Alright, 2 takeaways stand out. A recurrent transformer memory with constant time updates that stores a scalable set of embeddings, and clear gains in relative pose estimation and navigation over long horizons with modest compute. The broader signal is practical, mapping free goal localization for continuous robots. Thanks for listening. I am Alex, signing off from AI Research Roundup.